Okay, in this video we're going to learn how to use the ideal gas law to find the molar mass of a gas. Take a second to read this problem. Actually, I'll read it. You do not have this one in your packet. This is from the book. A large evacuated, and evacuated means emptied, a large emptied flask initially has a mass of 134.567 grams. When the flask is filled with a gas of unknown molar mass to a pressure of 735 torr at 31 degrees Celsius, its mass is 137.456. When the flask is evacuated again, that means emptied again, and filled with water at 31 degrees Celsius, its mass is 167.9 grams. The density of water at this temperature is 0.997 grams per milliliter. Assuming the ideal gas equation applies, calculate the molar mass of the gas. So the first thing I'm going to do here, and I would like you to do it too, pause the video and draw a picture of what we have here, and I will do the same thing. Okay, so hopefully you have pictures that look a little bit like this. I encourage you to draw pictures that will help solidify the information you have in your mind. You don't always have to do it, but you always do want to write down the information you were given. Here we had a lot of information, a lot of different masses, so with some pictures it just helps lay out what we have. Okay, we're asked to find, so I'm going to put this in black, we're asked to find the molar mass of the gas. And now I'm going to take an inventory of what we have, the information we have. So I'm going to make this a little smaller. And I'm going to see, okay, so I have a way to find the mass of the gas because I have an empty mass here and then I have the mass after the gas. So I can calculate the actual mass of my gas. So I'm going to write that down, my mass of gas, and I'm actually going to go ahead and calculate it with my calculator. I'll pause this. And I'd like to point out that we are working here, if we're multiplying, we're working with 6 significant figures, but I'm doing subtraction right now because to find the mass of my gas, I need to subtract the empty flask from the full one. And when we do subtraction, we take our significant figures to the place value where both numbers, so we're going to go out to the 1,000th place. So the mass of my gas that I find is 2.889 grams. So I have a mass of gas. What else do I have? I have a temperature. My temperature is 31 degrees Celsius, which I'll convert to Kelvin by adding 273. 31 plus 273 is 304 Kelvin. I have a pressure. My pressure is 735 torr, and if I want to convert that to atmospheres, I'll come back and do that in a second. If I use the ideal gas law, I'll probably want to convert it to atmospheres. So because my R value is 0.0821 liters atmospheres over mole Kelvin. You don't have to memorize that. That's always on your equation sheets. So let's go ahead and convert this to atmospheres. There are 760 torr in every 1 atmosphere. So if I do this math, I'm working right now with 0.967 atmospheres. And here I have 3 significant figures. So my answer is in 3 significant figures. When we multiply, we do our significant figures with the least number of digits. And you can assume that over here this is 760 with the decimal. So I have a temperature, I have a pressure, I have a mass, I have an R value. Those are looking promising because I know I have this formula, PV equals nRT, and the molar mass of the gas, let's just go back, that's what we're asked to find. Let's think of how we would find that. I should have done this first. If we needed to find the molar mass of the gas, what is the molar mass of the gas? Well, the molar mass of the gas is equal to the mass divided by the number of moles. I should have done this first. So I know the mass of my gas. That I know. What I don't know is the number of moles. That's what I need to find out. And the ideal gas law allows me to find number of moles. So I think I'm going to want to use this ideal gas law because then I can plug that in here and I'll divide the mass by the number of moles and find the molar mass. So let's go back to this equation and check off what we know. We know our pressure. We know our R value, we know our temperature, we're going to be looking for number of moles, So actually I could rearrange this. N equals PV over RT. I know my pressure, my R, my T. I do not know my volume. Now this explains why they gave me this information about filling the flask with water and the density. First I was like, why are they throwing water into this? But from the density of water, which is measured in units of mass per volume, and I'm looking for volume, and from the mass of the water, we can find the volume of this container. So let's do that. Let's do that. We have no room left. I'm going to copy, hold on a second. Okay, on this next slide, we're going to find the density of, we're going to find the volume of the container by using this density data and the mass of the water. So we know that the flask filled with water was 107.9 grams. When it was empty, it was 137.456. So we can find the mass of the water, mass of H2O, using subtraction. And the mass of the water, it's 167.9 grams minus 137. Oh no, I subtracted the wrong thing. It's going to be 167.9 grams minus the empty flask. Let's do it again. And so the mass I come up with is 933.333. And since it's subtraction, I'm going to take it out to the thousandth place. Oh no, wait, I can't do that. It's subtraction, and the place value here is in the tens, whatever this is, the tenths place. So I have to, my significant figures are just going to go to there. That's the mass of my water. Now, I need to find the volume. I'm looking for volume. If I multiply mass by density, I'll be able to get volume, because if you have mass and you multiply it by the density upside down, which is in grams per milliliters, you'll get milliliters. So I'm going to take this density right here and use it. At 31 degrees Celsius, the density is 0.997 grams per milliliter. So that means 0.997 grams are in it for every 1 milliliter. You could also set this up as a proportion. There, I'll do that here. 0.997 grams are in every 1 milliliter of water. So if you have 933.3 grams, your volume is X milliliters. We're going to just multiply here. So grams cancel out with grams. We're going to 933.3 times 1 divided by 0.997. And the volume turns out to be 936.1 milliliters. And it'll eventually, it should be in 3 significant figures, so I'm just going to use 936. Now, when I go to put this volume into my formula, it has to be in liters, and right now it's in milliliters, but my R value uses liters. So let's convert this to liters. We'll do it in purple up here. If we have 936 milliliters, there are 1,000 milliliters in every 1 liter. So, and that's meant to be an equal sign. So 936 times 1 liter divided by 1,000 equals 0.936 liters. So that's my volume. So I'm going to write that down here. Volume equals 0.936 liters. And now I can plug these numbers, 0.936, my pressure of 0.967 atmospheres, my temperature of 304 Kelvin, into my ideal gas equation, which is right here, and find out my number of moles. So let's do that. So I'm going to do that. I made myself more room. So I have, we'll use a different color. What color should we use? Well, we'll use black. Never mind. N equals 0.967 atmospheres. 0.967 atmospheres, then I had to put in volume, which was 0.936 liters, and then my N equals PV over RT. This is my R, 0.0821 liters atmospheres over mole Kelvin, and my temperature is 304 K. I can cancel my units. I have atmospheres in numerator, denominator, liters numerator, denominator, Kelvin in the numerator of my denominator, and the denominator of my denominator. And my units are moles, but that's in the denominator of the denominator, which really means it's in the numerator. When you divide by a fraction, it becomes on the top. So I'm going to pause and do this math and find out how many moles we have. And I find out that we have 0.036 0.226. I'll write 4 significant figures now, away, but eventually I'll round it to 3, because in here we have 3 sig figs, 3 sig figs, 3 sig figs, 3 sig figs. Now remember, the question was, circle it in red, the molar mass of the gas. And to find the molar mass, I have to divide my mass by my number of moles. I had my mass all along, after I subtracted this from this, and now I have my number of moles, so I can plug these two things, I'll circle them in red, into this equation here and find the molar mass. Let's make everything, let's give ourselves some room. Smushy, smushy. See, this is where things get a little confusing. Smushies. I don't even know what that was supposed to be circling. So we have molar mass equals mass over N, which equals, my mass was 2.889 grams divided by 0.03626 moles. So my molar mass comes out to be 79.67 grams per mole, which I'm going to round to 3 sig figs, 79.7 grams per mole. So now I know the molar mass of my gas. I don't know the empirical formula, so I don't quite know what it is yet, but I do know the molar mass. That is how you can use a problem-solving strategy in the ideal gas law to answer a question.